In our last video we studied the quadratic polynomials. Let's now study the cubic polynomials and then move on to rational functions. We talked about functions of the form x minus h. So in this case 3 is our number h and is greater than 0. So this it's telling us that it's going to be a shift to the right. A shift to the right of the original function f of x equals x to the power 3. So plotting g of x, it's actually very simple. All we have to do is first plot f. We know that the plot of f is something like this. So to plot g, all we have to do is move h units, in our case h equals 3, to the right, and then draw the exact same plot of f, but using 3 as the origin. So our function g would be something like this. Let's say we now define the function h of x equals the absolute value of x minus 3 to the power 3. So h of x is actually the absolute value of g of x. To plot this function, let's think for a minute about a number x0. x0 is such that g of x0 equals minus 1. So x0 would be a number such that g of x0 is minus 1. Then x0 is this number here in the x-axis. Now what h does is h of x0 will be the absolute value of g of x. So it's the absolute value of g of x0. We said that g of x0 was minus 1, so this is the absolute value of minus 1, which equals to 1. So what h will do is grab this number and move it to a positive number, 1, to the opposite. And h will do the same with all numbers in the plot of g. So then the plot of h will, for all the negative numbers, will be the symmetrical line in the positive axis, and for all the positive numbers, for g, is going to be the exact same function. So the orange line is h of x, and the green line is g of x. Now let's talk about rational functions. A rational function is of the form p of x divided by q of x, where both p and q are polynomials. The most common example of a rational function is f of x equals 1 over x. We know that the domain of this f is the set of all the real numbers except 0. And we also know that f of minus x, which is 1 over minus x, this equals minus 1 over x and equals minus f of x. So what this is telling us is that f is symmetric with respect to the origin. And if we say that y, a number, equals 1 over x, then multiplying by x on both sides we get that x times y equals 1. And then this tells us that both x and y have the same symbol, because it's multiplication is a positive number. So when we plot the function, we know we'll have to draw in this plane, because here both x and y are positive, and in this other plane, because here both x and y are negative. This function is very simple to plot when we make a value table. I'm gonna leave that as an exercise, and I'm gonna just make the drawing. The function looks like this. And as it is symmetric with respect to the origin, then in the negative section it would look the exact same thing. So what this symmetry is telling us is that if we graph, say, this point here, and let's say that this point is the -1/2 -2. Well, we know our function is symmetric with respect to the origin. So if we draw a straight line from this point and passing through the origin, we get to this other point here, and this point is going to be the 1/2, 2. Another thing to notice is this section in the plot right here. We know that there is no x such that f of x can be 0, because then 0 would be equal to 1 over x, and this is impossible. We do know, however, that when x is big, and I'm gonna draw it like this, when x goes to infinity, this is when I move in this direction, then 1 over x will be as small as possible. It won't be 0, but it will try to approach 0, and this is what we see here in the plot. When the line goes as close to 0 as possible when we move to the right. This is a concept called limit, and we'll learn more about this in the future. For now, let's just stay with this intuitive idea. When this happens, we call it an asymptote. And in this case, it's a horizontal one. Well, if you pay attention, you can notice that the same happens here. When x goes to -infinity, then 1 over x will also try and go to 0. So we also have a horizontal asymptote here. And what about this section of the plot? Well, in this case, x is trying to go to 0. We said that the domain of f was defined for all x except 0. So what's happening here is that when x goes to 0, 1 over x is going to be bigger and bigger as we get closer to 0. So then 1 over x will try and go to infinity. And that's what's happening here. When x goes closer to 0, the plot goes to infinity. This is also an asymptote, but in this case it's a vertical one. And the same happens here. When x goes to 0, but from the negative numbers, here it was from the positive numbers, then 1 over x goes to -infinity. So note that we know a lot about the function 1 over x. Let's try and plot other functions like g of x equals 1 over x minus 3. Well, if we take again the f we have, then we notice that f evaluated in x minus 3 is exactly g of x. So what we can say here is that this number 3 is an h, and because we wanted the representation on the form f of x minus h, and 3 is greater than 0, so again we have a shift to the right. So to draw g, let's first draw f. F is the function we just studied. I'm gonna draw it like this. Now to draw g, we have to move 3 units to the right. Now what I'm gonna do is draw a vertical line here in 3, because now g will be symmetric with respect to this point right here. This will be our new origin, the point 3, 0. So with this, it will be easy for us to draw g. It will be like this. So if now I remove all these other lines we draw, then we get the plot of g. And this function has the same properties the original one, f, had. So again we have two horizontal asymptotes in 0, and we have two vertical asymptotes. But as the shift was towards the right, then the vertical asymptotes were also shifted 3 units. Now the vertical asymptotes are in x equals 3. And this is because g of x will be defined whenever x minus 3 is different than 0. And this is when x is different to 3. So when x equals 3, g of x is not defined. And that is the definition of a vertical asymptote. Let's do one more example to show rational functions. Let's say we have f of x equals x squared plus x minus 6 divided by x minus 2. Both this numerator and denominator are polynomials, so f is a rational function. And whenever we have something like this, a long polynomial and a very short one, then the best thing to do is to factorize the long one. So to factorize x squared plus x minus 6, we multiply x plus 3 times x minus 2. And this was all divided by x minus 2. So now here we have x minus 2 divided by x minus 2, and we can just cancel them out, right? So then this equals x plus 3. And this is correct, but not quite, because here we are cancelling out. Cancelling out is dividing by, in this case, x minus 2. And we can do this whenever x minus 2 is different than 0. So, yes, f of x, our function, is equal to this, and is equal to x plus 3 whenever x minus 2 is not 0. So, these two functions are equivalent, and we're gonna see this in the plot. Let's draw the plot of x plus 3. X plus 3 has the root on minus 3 and the y-intercept in 3. So now we have to join these 2 points and this is our function. But in this case, when x equals 2, this is a valid point. But here, x equals 2 is not. And then what we have to do is go to x equals 2, and in the value of our function, which is this one, we're gonna draw a hole. So in this section, the plot is not defined for f. G was the straight line. This is G. G was the straight line, but f has a hole in x equals 2, because f is not defined for x equals 2, because then the denominator would be 0. So this is something to watch out when we work with rational functions.